In this video, I want to show you how to calculate the power of a test of a proportion, specifically when we are doing an exact test of a proportion using the binomial distribution. So if you've not learned about the binomial distribution yet, you probably want to go back in this series and find the video on the binomial distribution and maybe even those before it, because they all lead up to the binomial distribution. We're going to use that distribution to calculate the power of a test of proportion, just as we use it to do a hypothesis test of a proportion. First, let's define power. The power of a hypothesis test is the probability that the test correctly rejects a specific null hypothesis when a specific alternative hypothesis is true. Note the term specific used twice here, once for the null hypothesis and once for the alternative hypothesis. That's important if you're going to calculate power. Here, for example, we have two hypotheses that are quite common when we're looking at proportions. The first one, the null hypothesis, is that pi equals 0.50. If the probability of success is 0.50, it's about the same as flipping a coin. That is, it's telling you that your treatment or whatever means you're using in order to invoke success in your participants does not seem to be having that effect. In order to have that effect, we would look for pi to be greater than 0.50. But consider these two hypotheses, how they are different. With the null hypothesis, we can completely determine the distribution of the test statistic. The test statistic would be the number of successes in n trials. And if you have pi of 0.50 and you know the number of trials, you then know exactly which binomial distribution to use. You completely determine the distribution of the test statistic. Because of that, we refer to this as a simple hypothesis. By contrast, our alternative hypothesis, which says that pi is greater than 0.50, we do not know the distribution of that test statistic because it again is going to have to be determined by a specific value of pi and a specific n, sample size. Well, we know n, but here we do not know pi because it can be anything over 0.5. It could be 0.51. It could be 0.60. It could be 0.65. It could be 0.73. Because of this, this is known as a composite hypothesis. But in order to calculate power, we're going to have a specific hypothesis. We're going to end up using two binomial distributions, and we have to know what they are. We now know what the binomial distribution is for the null hypothesis. We do not know what the binomial distribution is for the alternative unless we change it to something like this. Here, pi is equal to 0.65. Now, that is still greater than 0.50, but it is a specific value that's greater than 0.50, the value of 0.65. Note that the further we get away from 0.50, the less our successes seem to be the result of a coin flip and more the result of something that we're actually doing with our participants. So we could call this difference between 0.50 and 0.65 the effect size, the effect of our treatment, or the effect of whatever we bring to bear on success for our participants. The further away we are from 0.5, the bigger the effect size. And this would work in both directions. It may be that having success is not a good thing. Remember, success can be defined any way we want it. Success could be something like a student failing a test. I don't know why you would call that success, but it's allowed in statistics. And so if we wanted pi to become a smaller value, we could do that as well, and the effect size would be bigger and bigger as we get further away from 0.5 in the smaller direction. But here I'm going to keep it simple. I'm going to say, let's suppose that larger values of success are what we're looking for. That makes sense, at least as far as the English language goes. So this is our effect size. Now, effect size is going to affect power. We could have set pi to be 0.60. That still would have been an alternative hypothesis above our null hypothesis of 0.50, but the effect size would not have been as large, and consequently, the power would not have been as large. When we have a larger effect size, we have more power. But effect size is not the only thing that influences power. The sample size influences power. The more observations we're able to make, the higher our power will be, all else being constant. That is, if we keep that effect size at 0.65 and increase the sample size, we're increasing our power. Similarly, if we increase the nominal type 1 error rate, alpha, then our power also will go up. Now, the nominal type 1 error rate is typically set at an industry standard, such as 0.05. So this is probably not a desirable thing to do in most studies. However, you should know that if we increase that error rate, we can increase power. If you leave that error rate constant, you can increase power by either increasing the effectiveness of a treatment or increasing the sample size. Here are the steps to calculating power. First, we have to determine the specific distribution of the test statistic when the null hypothesis is true. In the case of a proportion, we know the distribution is a binomial distribution based upon pi under the null hypothesis, as well as our sample size. We then determine the rejection region and critical value on this distribution. What would it take for us to be able to reject the null hypothesis about that particular value of pi in favor of the alternative hypothesis? We determine the number of successes that it will take in order to reject the null hypothesis, and the borderline number of successes for rejection would be called the critical value. Anything over that in a one-sided upper tail test will also be in the rejection region and lead us to reject the null hypothesis. The third thing we do is determine the specific distribution of the test statistic when the alternative is true. This is why we need a simple alternative hypothesis rather than a composite, because we have to determine this specific distribution. And again, if we have a single value of pi in the alternative and we know the sample size, we can determine which binomial distribution this is. The fourth step is to determine the probability of obtaining a value in the rejection region if the alternative is true. Remember, we create that rejection region using the null hypothesis, but then we determine the probability of being in that rejection region, not if the null hypothesis is true, but if the alternative is true. And when we do that, we have found the power. This probability is the power for a test of the null hypothesis when that specific alternative hypothesis is true. Now, this is going to make a whole lot more sense if we have an example, so let's go there. First, we want to determine the specific distribution of the test statistic when the null hypothesis is true. Let's suppose we have a null hypothesis of pi equals 0.50, and we're going to make 15 observations. That is, our sample size will be 15. We can determine the binomial distribution. Here's a picture of it. Notice that x, the number of successes, ranges from 0 to 15, at least on the picture. I'm only showing you x from 7 to 15 along with the probability of each of these values of x just to save space. Note, for example, that the first probability of 0.196 is the probability that x is 7 if pi is 0.50 and we make 15 observations. The same is true for the value of 8, all the way down to a value of 15, in which the probability of observing 15 successes, if indeed the probability of success is 0.5, is only 0.00003 if we're making 15 observations. Now we have to determine the rejection region and the critical value on this distribution. Remember the rule. What we want to do is we want to look at values that are unlike the null hypothesis and more like the alternative hypothesis. Our alternative hypothesis here is larger than the null hypothesis, so we're going to go down to larger numbers of successes, starting with 15 and going backwards, trying to get as close as we can to our alpha of 0.05 without going over. And so we start calculating, and we might try some of these. Perhaps we calculate the probability that x is greater than 11. We find that to be 0.059, which is greater than our acceptable error rate of 0.05. So now let's try 12 or greater. The probability of 12 or greater is only 0.018, or about 0.02 or 2%. That's substantially less than 5%, but that's a typical consequence when you're dealing with discrete data. You're not dealing with a continuum of values from 0 to 0.05 and beyond, but rather you're taking things in jumps. And here we jumped from 0.059 all the way down to 0.018. So 12 is our critical value. If we took any value less than 12, we would be exceeding our nominal type 1 error rate. 12 is the critical value, and our rejection region goes from 12 to 15. So we've now determined the rejection region and the critical value on this distribution. Time for the next step. Determine the specific distribution of the test statistic when the alternative is true. Well, we chose an alternative of 0.65. So we're going to do the exact same thing we did a moment ago. We're going to create a binomial distribution, this time, however, using a pi of 0.65 and a sample size of 15, and here it is. Notice how the high point of the distribution has shifted to the right, as we would expect, because there's a higher probability of success. Once we've determined that specific distribution, we now have to determine the probability of obtaining a value in the rejection region if the alternative is true. Careful, we are not constructing a new rejection region. The rejection region is for the null hypothesis, not the alternative. So when I say we have to determine the probability of obtaining a value in the rejection region if the alternative is true, it's the same rejection region we used for the null hypothesis, and that was 12 and above. So if we calculate the probability of getting 12 or more successes when pi is 0.65, that turns out to be 0.17. This probability is the power for a test of the null hypothesis when the alternative is true. So the power for testing the null hypothesis that pi equals 0.50 against the specific alternative hypothesis that pi equals 0.65 is 17%. That is, there's a 17% chance that if the probability of obtaining a participant who is going to be successful is 0.65, that we will reject the null hypothesis of 0.50. If the probability of success is 0.65, should we reject the null hypothesis of 0.50? Absolutely. But the chance of that happening is 17%. This is not high power. This is not good. So we need to talk about what can we do to increase power, and more generally, how do we use power when we conduct research? I'll talk about that in the next video.